So hello everyone, my name is Týna, and together with my awesome partner Lubo, we would like to give you a bit of an introduction into how to work with the satellite data, what they are, where you can find them, and how to actually do something with them in the Python. We both work for the company called EOX, so that's why we have there the company colors, because we are usually terrible in designing pretty slides, so this is a little bit of a help. And let's get started. So before we jump into more of a setting a ground and some common terminology, how many of you ever worked with the satellite data? Wow, that's a good number. That's very nice to see. So cool. But for those who haven't, so what are the satellite data? Obviously, they are captured from space. We have many satellites. But today, for the sake of time, we will be talking about Earth observation data, which are the images taken of the Earth, so not looking further into the universe. And more specifically, we will be also talking only about the optical data, and more specifically, Sentinel-2 mission. There are new missions launched every year, and for example, European Space Agency is launching extreme amount of very cool scientific missions measuring, for example, magnetic field or a wind from a space. Maybe you saw 2 weeks ago how the satellite burned in the atmosphere, which was very cool. And so we will for now skip completely other data types and just focus on the optical one, so don't be disappointed. Since we are talking about the optical data, what are the bands? The band is a completely basic terminology, so let's get started with that. Basically, a band is a data collected from a single wavelength sensor. So commonly we have a RGB data. So red, for example, is one single band of the imagery which we are working with. We have many types of data, as I already mentioned, so they have a different resolution. So Sentinel-2 data have a 10-meter resolution, but there are much more precise data from private companies, which obviously cost money. What I didn't say is a Sentinel-2 mission is launched by European Space Agency, and the data are publicly available for everyone, so that's why we choose them. There are also different processing levels, which we will be talking later. There are different instruments, meaning different sensors, different types of data. Also importantly, there are different revisit times. So revisit time is how many times single space on Earth is captured by the satellite. So it can be 2 days, it can be 1 week, and this frequency can really affect our workflows and what data actually we choose for our analysis. We also have a different bands available. So as I said, standards are RGB for the optical data, but we can have a yellow band, we can have a near-infrared band, we can have many more, and based on these compositions, we again need to select the data we are interested in. On the image, which is a bit outdated, as you can see how the satellite data are basically a new thing. So the volumes of the data are rapidly increasing, and comparing from 2016, where the first Sentinel-1 was launched, to current state, where we have so many missions and multiple satellites at the same time. So for example, we have 2 satellites from a Sentinel-2 mission, which means we can get a more frequent data updates. That's pretty cool, but also it brings new challenges. Before we get into the data, actually, it's important to say that basically everything is, in the end, a NumPy array of data. So it's just numbers measured of something. So it's not a dark magic, it's not a rocket science, it's just NumPy arrays. So now you know what kind of data we have, and let's talk about the possible applications. They are limitless. The most common ones is, for example, land classification, where we are trying to determine if the surface on the planet is a road, or if it's a field, or if it's a building. We have a crop type monitoring, which you can see here on this image, where we are trying to detect if the crop type identified on the field from satellite data is actually matching a farmer's declaration. So if he says, I'm growing here pumpkins, if it really actually is a pumpkin field. We are doing the sea ice monitoring, so for example, we want to prevent another Titanic scenario happen. We are monitoring flooding, soil movement, forest monitoring for how does it change. And on the image here, you can see also the plane detection. The funny thing is that since planes are moving quite fast and RGB have a different wavelength, we actually see the plane as a 3 different spots, even though it is a single plane on this image. So the plane movement can be also detected from this.
I will describe a little bit on where and how to find the Earth observation data that you could need for your workflows. There are basically 2 types. If you are a common user and you are just generally interested, every data platform has got usually some kind of web interface or a web map client, which will allow you to set your queries based on what you see on a map. So you are interested over your hometown, you are interested over data over some time period, and you are generally interested probably in cloudless data. So because we are talking again about Earth observation data, and over at least most parts of Earth, there are usually clouds more than half of the time. This really matters. You don't want an image which has 90% of cloud coverage. Even though it was taken, it's stored somewhere in the cloud, you are not interested in it. And these are generally stored in metadata that are served together with the actual image files. There are multiple standards how to query the data, because the more standards you have, the more urge you have to create another standard which unifies the problems of all the previous standards. I have just named 4 usually used standards nowadays for catalog and API access to filter for the images that you want. The newest child on the neighborhood is called STAC. The abbreviation is for Spatiotemporal Asset Catalog, which has a JSON as the structure. It has levels like catalog, collection, and item. These are the 3 generic levels over which you are searching. Each item is usually that one scene taken from the satellite with some connected metadata together with it. The other 3 catalog search interfaces are more dated, but they are still commonly used on the platforms that serve the data. Well, we talk about platforms all the time. The 2 go-to places for the Sentinel-2 or any Sentinel mission would be the Copernicus Open Access Hub, sometimes also named Sci-Hub, SCI Hub, which is the first place where the Earth observation data from the Sentinel satellites will appear. It usually takes a few hours from the point in time where it was really captured from the space, or up to 1 day. But after it really appears on this Sci-Hub, all other platforms which either mirror it or that take the data from there will also start to download the data. The data is completely public for you. If you log in to Sci-Hub, there is just a certain rate limiting if you start to spawn thousands of downloads. Unless you are a privileged user, there will be some throttling in. Second place where you can go to is currently in development. That is the Copernicus Data Space Ecosystem. It's a new platform that is being built. It has a huge potential, and they are adding features as we speak. The last place is that the big 5, so Microsoft, Google, Amazon, all have got their mirrors of the Sentinel data. They usually provide it either in the same format as the original platform or in the, let's say, better formats. This is an example of a search interface that I described. It's a simple catalog client. On every platform, you will see something similar. On the left side, you can see the spatial filtering and the time filtering and metadata filtering. This is where you specify what you actually want to not fetch information about thousands or tens of thousands of products that were taken over that area. On the right side, you see something called a quick look. which each satellite product has. It's a small scale, let's say 100 by 100 or few hundred by few hundred pixels image, usually in a PNG, that is simply for human eyes to view and to get a little bit of overview how the more resolution version of the satellite image looks like. What is also interesting is the footprints. So you can see that the products have got really various footprints. It's sometimes quite bizarre, and it's some kind of different geometry. I have an example how you can search through a stack catalog. I will not be running the code. I will just show you how it looks, because sometimes it can take quite a lot of time to get the data. But there is a Python package called PyStack client, which allows to interact with the stack catalog. So we define a catalog entry and connect it to an endpoint. Here I'm connecting to a AWS endpoint from Earthsearch, which has Sentinel-2 data and a lot of other data. So first I need to list the collections. So there is the first step where you get the collection that you're interested in. For us, it's going to be the Sentinel-2 L2A. And then you can initiate the search on that catalog based on your query. For us, it's going to be a bounding box over Prague with 2 weeks of data of this month. And you get the list of items. There are going to be 21 products that were taken in the last 2 weeks over Prague. Now, what does such an item look like? It is a structure that can be converted, of course, to a dictionary, because we are working with JSON all along. And the important part is that each product has got some unique identifier and then a set of properties, set of properties that define how the observation was made. This whole list is truncated. The list of properties is much larger. What is important are the data themselves. Those are the ones that you are usually interested, and these are hidden in the assets of the item. And you can see that there are multiple assets here in this product, and those are per band files that are connected. So I, for example, am interested in the red, green, blue band, or here I just printed how a single green band information looks like. And it is a connection to the actual file, so it's in the href attribute, lying somewhere on an object storage, and all the metadata that are linked to this file, which allows, again, for better search and better filtering. The thumbnail is also, the thumbnail is something I already talked about. It is the PNG visualization of the product for quick visual reference. Data formats. It is known that there are multiple, and have been in the past, multiple data formats. And the reason for this is usually who is interested in the data. And you always need to take care about size, so storage size, versus the utility. The data providers are usually more worried about the storage size, so they need to worry about compression, while we as users are more keen to use them in a cloud-optimized way, so we want to read them efficiently. We are interested in the read access. Which means the cloud-optimized data need to have overviews, which are a lower scale version of the original image. And they need to have some headers, which allow you HTTP range requests on the products themselves. We are generally working with GeoTIFFs and JPEG 2000 for optical imagery. Regarding data processing, we usually, as users, do not really need to care about reformatting and other steps, but general operations that you can do with data is, for example, reprojection into a different coordinate system, or clipping by geometry, or merging bands together into one single file. A small demonstration of that is using the package called Rasterio, which is a set of Python functions and Python tooling around the popular library called GDAL. What this example does, it fetches a geometry of Austria, and we are using that to clip our satellite image. So we first parse the GeoJSON, get the correct geometry of Innsbruck, and we fetch the data from an object storage again, open it with the Rasterio as a data set, and this is all loaded lazily, so at this point it's not that the whole file will be downloaded, and you can use the generic pie plot functionality of Rasterio that allows you to quickly visualize the data using the common color scales. And the last part is, for example, you want to apply filter. So here we are really already working with the NumPy arrays and directly masking the data out.
Cool. Now you have your data, so it's time to do some Earth observation data analysis. So as you probably know, the data scientists are very into complicated architectures. That's not so much a thing yet in the Earth observation data science. It is becoming, but you will usually find out that the currently used architectures are a bit outdated or a bit behind the rest of the world because there are many issues. What is commonly used for optical data are CNN-based architectures, because we are basically talking about images. The most common tasks performed are a classification and a detection. Classification of different lens types or a detection of the harvest event happening, for example. The important thing to mention is that we are basically talking about big data processes even if we are talking about a single image, because a single Sentinel-2 image usually have a size of 600 megabytes, which already takes a lot of memory consumption just to process that image. So we have large volumes even for small scales of processes, and there needs to be a different solution. So as Lubo was mentioning, the correct selection of your area of interest and the data you are only interested in is a key to make your processes as cheap as possible. There is another issue, and that's never enough of a training data, because not so many people are keen to labeling what they are actually seeing. It is a new data, as you can see, we are collecting more and more lately. And specifically, it's also very hard for human eyes to detect on the 10-meter resolution what is actually happening there. So for that, we are many times using other data. So for example, if you are trying to detect wind power plants, we have them somewhere because there is some electric plant company collecting these data. So we can double check if the data are correct. The common pitfall is the no data values. No data values are different for every data type. Sometimes it is a 0, sometimes it is a minus 9,999, and it's very hard to know which no data value was used for every product. So this is like 90% of the errors happening because people didn't filter out correct values. There is a big but. For many tasks, basic indices are used. Indices are a computation, basically algebra between different bands where we are trying to get some information highlighted or find out. They are still in many cases enough because, for example, as I will be showing in a second, we have an index to visualize the vegetation. So, or they are used as another source of data coming as an input into the more robust data science pipeline. So these indices are still very powerful and still should be considered. So as mentioned, there is an example of NDVI index. NDVI stands for Normalized Difference Vegetation Index, and is computed as a ratio between a near-infrared band and the red band. As you can see on this image, the values are in theory ranging from -1 to 1, but usually they are going from 0 to 1, where around 0 values means no vegetations. This is extremely useful for harvest detection. So we can see that on the field, which is completely red, the harvest probably happened already. It is not so easy to just based on this decide if the harvest really happened. So this is usually one of the many data inputs coming into that. But it is a very simple algebra providing a very cool result. Now, since I mentioned that we are usually enhancing satellite data with and other sources, let's talk about the data cubes. Data cubes in Earth observation are not only as a data storage, but usually referring to data together with a temporal dimension. As Lubo mentioned, we have a latitude, we have a longitude, but we also have a time. So we need to somehow put together the time series of the data captured over months or years, and maybe at another layer. So maybe we are interested in average rainfall or average temperatures over the field, so we know what is happening there. So maybe we also have some in situ data from a agriculture event, and we can all put it together and create a data cube. Data cubes are very powerful and very cool buzzword to use when you are working with the satellite data. So let's look into how to actually do the NDVI computation in the Python. I will be using here a package called Xcube, which is a wrapper over the X-array. X-array is a standard Python package for working with the data cubes, and this is just an extension to nicely work with the satellite data. So similar to Lubo's example, we again need to select the bounding box. I'm selecting a 30-day period, and I also am selecting a resolution. Here I'm interested in 10 meters precision. Then the main step is a cube definition, and there I'm choosing Sentinel-2 L level 2 processing, and I'm here interested only red band and the near infrared band. Band 4 is the red, band 8 is a near infrared. This is a thing you just need to find in the documentation. I'm interested in the time period of 5 days, so I do not have to collect so many data. As Lubo also said, we are using the lazy loading, meaning that the data are not downloaded until you specifically requested some results from it. So everything is happening not on your platform, so this limits a lot of data traffic. You can visualize the downloaded data cube, and you can see that we have here a band 4 and the band 8 as the data variables. We also have here a couple of indices, as I mentioned, and we also have a lot of attributes where we can find out what actually happened to the data. So we can double check that our processing levels are actually what we are really interested in. Specifically, I can also look into the band 4, which is the red band, as I said, and looking at the attributes, I can also find here the wavelength, the resolution, which is matching my desired resolution, and another data, and most importantly, double check what values I'm getting, because here I'm getting numbers, but in some cases I can get something else. I can also display my data. So here I'm using a nearest method, meaning I'm taking the value from a nearest pixel for each location I'm interested in, and I'm just using basically a function wrapped in the matplotlib. So you can see the area in the north of Germany, close to city Kiel, and the completely dark area on the top is a sea, and below are the fields and the cities. I could be doing the same for the band 8, but we do not have enough time, so let's just compute the NDVI index. The NDVI index is computed as a ratio between these two bands, and I just store it as another parameter into the cube, and I can just visualize it. Here I have a units set as unitless because I just said so, and I can already see my values there. I can also compute the time series of these based on the nearest method and see that the index of the value is actually changing. But the most cool thing is actually to see it, to see the data. So again, I'm using the nearest method to get the nearest value, and I'm choosing the 21st of May from 2018 to visualize the data. And you can see that the sea, so on the top, has a value around 0, which means no vegetation. But the lower we get, we can clearly see the fields, and something green is happening there. That's why the scale is commonly associated with the NDVI index. For analysis, to actually conclude some results, we need to display them in some relation. So here I'm displaying all my computed NDVI indexes for all the times I have selected. As mentioned at the beginning, we have a cloud issue with the optical data. And you can see that on the 10th of June, we can't see anything and make any conclusions from that. That's why usually a Sentinel-2 are not so good alone, because if they would be doing some harvest event there, we would not be able to notice that. Also on the 15th of June and still on the 20th of June, not enough cloud coverage to see the results. So these are the simple visualization, and Lubo will tell you more about the cooler ones.
We don't actually have any cooler ones. I just want to point out that a visualization of Earth observation data usually just means one thing, and that is to convert some original values, which are usually in unsigned integer 16 format, so the value ranges of 0 to 10,000 or something like that, depending on the satellite, and convert that to an RGB space, 0 to 250, 8-bit data that we visualize. This is the only part of the magic that we do. It was already mentioned that different band combinations can make different highlight, can highlight different data. For example, false color using the near infrared is generally visualizing the vegetation much better. There are two ways how to visualize Earth observation data. One is you use a server underneath, and it serves you tiles, map tiles, usually 256 by 256. Second method is you serve the data directly, and you do the visualization on the client, which is what this demo is showing. It is showing wind density map over Austria, and it is filtering the data on the fly, so the data were fetched once, the visualization then is applied on the data themselves. This is all for us. My key point from this is the data are really, really cool, and Týna will finalize with that.
Cool. So we have a cool game. If you want to play, it's called EOGuessr, where we are showing a Sentinel-2 image, and you can try to guess the location on a map based on what you see. If you want to know more, just find us. We will be here all day. The last thing on the end, we are looking for a DevOps engineer to work with me. So if you like the satellite data, we are looking for someone. And if you would like to connect with us on the social media, use the QR code. Thank you.